Yes, so it shows lecture 6, Gauss elimination method, chapter number 9. And last week we covered uh, almost half of this topic up to example 9.5. Okay, up to here. Okay, here. So we start from uh, slide number 27. Okay, pitfalls of elimination methods. So what are the uh, things by which we can not be successful? We cannot be successful with this elimination methods. So these things can be the possibility for the division by zero. So sometimes when doing the using the elimination method, we may come across this situation. So it can happen during both the elimination and back substitution that a division by zero can occur. So when this happens, the elimination method can fail. The second pitfall is the round of errors. So just like round of errors are common in almost every numerical calculations, but especially as we have already learned in those situations when we are subtracting two almost nearly equal numbers. And when, of course, we are dividing by a denominator with a very small value. The third pitfall is the ill-conditioned system. So this is because the systems where small changes in coefficients result in large changes in the solution. So this we will see in one example next. Alternatively, it happens when two or more equations are nearly identical, resulting a wide ranges of answers to approximately satisfy the equations. So since a round of errors can include small changes in the coefficients, so these changes can lead to large solution errors. So you can see that combined with the previous round of errors equation, if there is any small change into the coefficients of the equations, but as the result of those small changes in the coefficients of the system, there will be a large change in the uh, solution of the system. So that solution of the system, that system is called as the ill-conditioned system. So this we can see with the help of this example, ill-conditioned systems. So suppose if we have this system, x1 plus 2x is equal to 10 and 1.1x plus 2x is equal to 10.4. Okay, so and then for this system we say that this is an ill-conditioned system, but we want to illustrate it whether it is an ill-conditioned system or not. So for this, first of all, we will find the solution of this system by using these exact same values. However, in the second part, we will just replace 1.1, this 1.1 coefficient with the 1.01 coefficients. And then we will find the solution. Uh, and then we will see that these two solutions will be very much different from each other. Okay, so in the first case, when we are using this system of equations, the solution is 4 and 3. Okay, so these are just the two equations. We can easily find the solution by the Cramer's rule, so which is simply A22 B1 minus A12 B2 divided by A11 A2 minus A12 A21. So A11 times A21, okay, A11 times A22, sorry, and minus A12 times A21. Okay, so this is just simply a 2 by 2 matrix, so we can easily find its determinant. So, and then we can also find the determinants in the numerator and numerator, which are needed for x1 and x2. So easy solution for 3. Okay, so this is the solution for the case when we are using this coefficient 1.1 and then 1, 2, and then 2 over here, the solutions, the coefficients. But if we just change it, if we change just 1.1 to 1.01, so then what happens? So in this case, the solution will be 8.1. So now you can see that the solution from 4.3 to 8.1 is very much different. Okay, but the only difference between these two equations, between these two solutions, but the only difference between the equations is that we have used 1.05 instead of 1.1 in the equations. So there is not much difference in the equations, but there is a large difference in the solution of the equations. So due to this situation, we can say that the system is ill-conditioned system, and ill-conditioned systems can provide us misleading results in those cases when we are not using a very large number of significant digits for the answers, and when we when we want more accuracy, but due to the round of error we may not be able to achieve such kind of accuracy. Okay, so although if you want to see that if you want to just verify these solutions, uh, then we will see that these solutions will exactly satisfy these respective equations. Even the solution of one system of equation will also satisfy the other system of equations almost nearly. So for example, if you see that for one system, the solution was 4.3, okay? And for other system, the solution was 8.1. So if I take this solution 8.1, which is this 8.1 solution, which is for the coefficient 1.05. But if I want to check the solution of the first system of equation, for example, this one, if you want to check it with the values of x1 is equal to 8 and values of x2 is equal to 1, then we will see that it will almost satisfy these equations. Okay, so 8 x1 plus 2 x2 is equal to 10, plus 1.1 x1 plus 2 x2 is equal to 10.8, but it should be 10.4. But numerically speaking, 10.8 and 10.4 are not not very much different from each other. So we may be misled that this 8-1 solution, 8-1 is the, it may be the approximate solution of this system. But in reality, this is not the solution of this system. This is the solution for another system in which 1.1 is written as 1.01. So this, therefore, ill-conditioned system can also mislead you to the wrong solution. Okay, so do you have any questions about this? Hello?
No.
Okay. Next, we have example 9.7. Effect of scale on determinant. So evaluate the determinant of the following systems. So it is, for example, this system, A, 3x1 plus 2x2 is equal to 18 minus x1 plus 2x2 is equal to 2. And this system B, x1 plus 2x2 is equal to 10, 1.1, x1 plus 2x2 is equal to 10.4. So these are the two determinants. And repeat B, but with the equations multiplied by 10. So, but what do you mean? What does it mean? It means that first find this determinant of this system, and then multiply each of these equations, if each of these four equations, by 10 and find their determinant. And then what you can see. Uh, in this case, if you remember that if you uh, multiply any row of the system, any row of this system by some scalar, then the determinant is also multiplied by the scalar. So this we have already seen in the uh, linear algebra course. So the same thing will be happen if we multiply the equations by 10. So the determinant will be also multiplied by because there are two equations in this case. So the determinant will be multiplied by 100. So that we can see very easily. So in the first case, in this first case, so for example here, the determinant is 3 times 2 minus 1 times 2. Okay. So 3 times 2 minus 1 by times 2. So it will be 8. And in the second case, the determinant is will be 1 times 2 minus 1.1 times 2. So it will be minus 0.2. Okay. But when we multiply it by 10, so you will see that simply the coefficients will be multiplied by 10. So 3 will be 30, 2 will be 20, sorry, yeah, 10. 3 will be 30, 2 will be 20, 2 will be 20 over here, minus 1 will be minus 10. So what we can see is that 10 times 10 will be common from here, 10 times 10 will be common from here. So the system is actually multiplied by 100. So same thing will happen. The determinant will be also multiplied by 100. However, there will be no change in the solution of the system. Okay, no change in the solution of the system. Solution of the system will remain the same, although the determinant will be inflated by some scalar, uh, by that scalar, by the order of that scalar. But the solution of the system will remain the same. And this is true for both these systems. In the first system, which is a well-conditioned system, and the second equation, which is not a well-conditioned system, which is an ill-conditioned system. In both cases, the determinant will be increased by 2 order of the magnitude. 2 order of the magnitude means 10 to the power 200 in this case. So 10 is the multiplying factor, the scalar by which we are multiplying each system. So there are 2 equations, so 10 to the power 2, the determinant will be increased by 100. So before the determinant was 8, then after that the determinant will be 800. Before the determinant was minus 0.2, but after that the determinant will be minus 20. But here in this case, because this is an ill-conditioned system, as we have seen before as well, the determinant, and this is the ill-conditioned system, and for the ill-conditioned system, we see that the value of the determinant is almost close to 0. But by multiplying this system, by this system with 10, the determinant has also increased by 100 times, minus 0.2 times 20. But even that will not affect the condition of the system. The system will still remain ill-conditioned, and that we can also see by just simply changing some value of the coefficient slightly, and then we can see that there will be a large difference in the solution of the equations. So, so this example 9.7 is about this type of situation, that there is no change in the conditionality of the system. An ill-conditioned system remains an ill-conditioned system when you multiply that system with some scalar. So it has no effect on the solution, although the determinants are increased, but there is no effect on the solution. And if the solution and if the system is ill-conditioned, that system remains ill-conditioned even after that. So that was example 9.7. So is it clear? Right. Next is example 9.8. So in this example, we want to see another effect. That effect is called as the scale the system of equations 9.7 to a maximum value of 1 and recompute their determinant. So in the previous case, for example, we had these systems, okay? 3, 2, 18, minus 1, 2, okay? So it was asked, it has been asked in this example to us that we need to scale these systems. So for example, can you see this Excel, right? Can you see the Excel?
Yes.
Okay.
Yes.
3, 2, 18, minus 1, 2, and 2. So, for example, maybe I do it for this, and then you can even also verify for the second one. So, for example, in this case, it has been said that scale the system of equations in this example to a maximum value of 1, okay, and recompute their determinants. Okay, so let's go back to this Excel. So, yeah, here we have this system of equations, and it asks us to scale this system to a maximum value of 1. What does it mean? It means that we have these coefficients 3, 2, minus 1, 2. So we will change this system in such a way that the maximum value of the coefficient should become 1. So this can only happen if we take this first equation and then we divide it by the maximum value of the coefficient. So a main determinant, a main matrix for this system is this 3, 2, minus 1, 2. So in this first row, 3 is the coefficient with the maximum value. And in the second row, 2 is the coefficient with the second, with the maximum value. Okay, so what we can do is maybe we can divide this first row, okay, by its maximum value is 3. Okay, so the maximum value is located over here. So we are dividing it by 3. And then we can repeat it. Okay, so it will be 6. So 2 divided by 3 is this, and 18 divided by 3 is 6. And for this, we will divide each of these values by this maximum coefficient. Okay, so we will get 1 over here, minus 0.5 over here, and 1 over here. So in this way, we have scaled the coefficients. Okay, this is what we call as the scaling of the coefficients. And by scaling of these coefficients, what will be the effect on the determinant? Okay, so the determinant will be determinant D. Determinant will be, we can determine as what is the determinant? So determinant is this multiplied by this minus this value multiplied by this value. So this is the determinant. The determinant is 8. And what is the determinant for this? So we can just simply copy and paste the formula. So the determinant will be 1.33. So you can see that by scaling, you can see that there is a change in the determinant. So from 8, it has become 1/3. And you can see that from 8, it has decreased to 1/3. And how we can achieve from 8 to 1/3? Because what we have done was, we have divided this first equation by 3 and the second equation by 2. So 3 times 2 is 6. Okay, so in total, we have divided this whole system by 6. And if we divide 8 by 6, so we will get 1.33. So basically, the determinant is following this law that once you multiply or divide the row of a system, the determinant changes accordingly. Okay. So in this way, when we do the scaling, then the determinant will change. Okay, so we go back to this PowerPoint, and here we can see that the determinant will change. Okay, so the scaling, the changes to the system will change the determinant. However, will it change the solution of the system? So this is my question to all of you. By scaling, will the solution of the system change?
No.
Yeah. So you agree that the solution of the system will not change. But the scaling will have sometimes some advantages. Scaling may help us deal with the round of errors, and therefore, in many situations, it is helpful to scale the system. Okay, next is the next pitfall for the elimination method is the singular systems. So when two equations are identical, we would lose 1 degree of freedom. Okay, we would lose 1 degree of freedom. Uh, and be dealing with the impossible case of n minus 1 equations, one less equations for n unknowns. So for large sets of equations, it may not be obvious. Uh, However, the fact that the determinant of a singular system is 0 can be used and tested by a computer algorithm after the elimination stage. If a zero diagonal element is created, the calculation is terminated. So the singular system is that system in which uh, we will have two identical equations. So in those situations, then we will not have any unique solution from the system. So uh, for that n by for such an n by n system in which two of the equations will be same, that means two of the rows of the system will be same, will make the determinant of the system as 0. And in the Cramer's rule, if you see that if the determinant of the system is 0, then that is the case for the division by 0. So we cannot obtain any uh, unique solution for the system. Okay, so we have seen some of these pitfalls. So how we can remove those pitfalls. So one of the method for improving these techniques or the solutions is to use the pivoting method. Okay. Uh, so the pivoting, if a pivoting of the element is if a pivot element is 0, normalization steps leads to division by 0. So the same problem may arise when the pivot element is chosen is close to 0. So this problem can be avoided by partial pivoting and complete pivoting. So partial pivoting means, for example, if we have a system of equations and then we always bring that system of the equations, that equation on the top, which has the largest value of the coefficient. Okay, and then that largest value of the coefficient in the diagonal we make as the pivot, and then this can help us remove the errors in the calculation. So this can be done partially, or for more improved results or more control over the results, this can be even done for the complete system, completely for all the system. So let's see in this case, example 9.9. In this case, in this first equation, 0.00003 plus 3 is equal to 2.00001 is one equation, and in the second equation we have this. Here we can see that in this system, we have these coefficients, it's 0.003 and 1. And these two coefficients for x1 and x2 are at the diagonal position. Okay. But here you can see that this 0.003, 0.0003 can be a problematic coefficient. Because it is at the pivot position. Pivot positions are those which are at the diagonals. Okay, first row, first column, second row, second column, third row, third column, and so on. So these are the pivot positions. Okay, so for this system, the solution of the system is 1/3 and 2/3. If we don't use the pivot position in this case, then we may come across the errors. Okay. Uh, Although we can use Excel and then we can perform calculations with the double precision method, which will give rise to the exact solution of for these equations as 1/3 and 2/3 by using this exact same form, this equation. However, if we limit ourselves, to say 3 significant digits, okay, and then we increase to 4 significant digits and 5, 6, and 7, we will see that we will get different solutions. And of course, the absolute relative percentage error will decrease. So you see that for this system of the equation, the exact solution for x1 is 1/3 and for x2 is 2/3. Okay, these are the exact solutions, but not in the decimal form, but in the fraction form. Okay. However, if we restrict our calculations to 3 significant digits, so we will get x2, the value of x2 as 0.667, which is fine. Okay, because the value of x2 is 2/3, so which is not very much different from 2/3. So only the percentage error in 0.0000 something. Okay, but for the solution of x1, there is a large error. The solution, the x1, remember, the solution of x1 is 1/3. Okay, the solution of x1 is 1/3. But in this case, if we are restricting our calculations to only 3 significant digits, instead of 1/3, we will get a value of minus 3.33, which is 1099% difference from the absolute, from the true value. Okay, so it means that for such a system in which we have very large, some of the coefficients are very small, and comparable to that, the other coefficients are very big. And then we have the restrictions on this use of some significant figures. So we can get a large error in the calculations. So this error in the calculations can be reduced by using more number of significant digits. So for example, if we use the 4 significant digits, the value of x2 obtained will be 0.66667. Okay, so this is the um, this is an answer in 4 significant digits. The value of x1 will be 0.00000. Okay, okay, but still the original value, the correct value is 1/3. Still, it is 100% different. At 5th significant digits, the value of x1 is now only 10% in error. At 6 significant digits, the value of x1 is now at 0.33% error. And at 7 significant digits, the value of x1 is 0.333. So it is now 0.1% error. So in this case, we can see that as we are increasing the significant figures, the error in x1 calculation in this system is gradually decreasing. But you can realize that if we are obtaining the methods by using this form of the equation, if you're using this the numerical method, by this form of the equations, the solution is very inefficient. So that means we have to using a very large number of significant figures to get a very uh, not a very high level of accuracy. Okay. However, if you change this system to say like this, that means if we replace these two systems equations. So for example, if we make the first equation as the second equation and the second equation as the first equation, and then apply the elimination method. And in this case, by changing this, one will become as a pivot position. So one is a coefficient with the maximum value in this row, and this will come at the pivot position. And then if we apply the same calculations steps for the significant figures, so you can see that even with 3 significant figures, we get an answer of 0.3333. Okay, which is very much accurate than in the previous case. And then with the 7 significant digits, we get the answer of 0.333333. So the error is much smaller. So this is the solution which we have obtained by simply interchanging these two rows to these two equations, right? So this is the example for the pivoting. Okay, so whether it is a partial or full pivoting, it will be helpful. Okay, so pivoting methods is a useful method for improving the solution and improving the numerical calculations. Okay, so that was for the pivoting. Now the effect of the next example is the effect of scaling on pivoting and round-off. So solve the following set of equations using the Gauss elimination and pivoting strategy. Yeah, so for example, if we have this system 2 and then this one, if you can solve it by the Gauss elimination and the pivoting strategy, so then we can easily get the solution. And remember that if in this case, if we want to, the exact solutions are this 1.000002 and then 0.9999998. So that means if we adopt at least say 5 significant digits, 6 significant digits at least, then we can get this much level of accuracy. But if we are, for example, taking only 3 significant digits, so we will get the answer like this, which will be much different than the previous answer. If we, for example, if we get the answers like 1 and 1 in this case, because all these answers are 1 and 0.99, these are quite close, so their approximate answers are 1 and 1. But by applying some approximate method, if we can get these answers as 1 and 1, then that solution may give you a good enough results. So if we scale it, then what we can do is we can get this type of answer. So for example, if we scale this equation, so for example, this first equation, how we can scale it? Okay, so for scaling, what we will do is we will divide by 2. Okay, and we will we will divide by so 2x1 plus 100,000, x2 is equal to 100,000. So it is equal to, yeah, here it will be 0.00002. So that means we are dividing by 100,000. Okay, so first equation we will dividing by 100,000 and then it will become like this. From this equation now we can eliminate one of the x1 and x2, and we can get the approximate answers are 1 and 1, which is a good enough result in this case, because this answer is not much different from the exact result. So this example 9.10 shows that even if we are limited by the significant number of digits, but we are using the scaling and pivoting methods, we still can get a good enough results. Okay, we still can get a good enough results, just like as we have done in this case. X1 is equal to 1, X2 is equal to 1. So scaling and pivoting are good techniques for getting the results. Okay, and similarly for an ill condition, the case number problem C, we can see that the scaled coefficients, even if, for example, if you don't scale it, okay, in part C, it has said that even if you don't scale it, but you just use the pivoting method, but still it can be very helpful, and then you can get the good enough approximate results of 1 and 1. Remember that the exact results are x1 is equal to 1.00000 something, and the x2 is 0.99998 something. Okay, but both 1.000 and 0.9998 are close to 1. So their good enough results are x1 and x2 is equal to 1. But these good enough results we can obtain just by using low number of significant digits and using the uh, pivoting and scaling techniques. Okay, but if you have to choose from the pivoting and the scaling techniques, I think the pivoting technique is the most useful technique, and the scaling technique. Scaling technique can be sometimes helpful, but the pivoting technique is the one which is the most useful technique. Okay, do you have any questions?
No.
All right. So, well, that was previously we have talked about the Gauss elimination method. So, the more improved technique. In the Gauss elimination method, we have then two types of variations. One is the naive Gauss elimination, and the other is the improved Gauss elimination. By improved Gauss elimination, I mean you will always use the pivoting coefficient to pivoting coefficients to uh, improve the solution. So the Gauss Jordan elimination method is a method in which we use all of these things together, but we apply these situations, these improvements as a whole, and then we get the solution directly. Okay, so we don't have to do the back substitution to get the solution. Okay, so suppose in this equation, okay, so we have for example, this is the system of the equation. Okay, so we have this system of equation. I have already worked out over here. So this is the system of the equation. Okay, 3 minus 0.1 minus 0.2. You see over here. Mm, yeah, 3 minus 1. So this is the same system of the equation. So if we want to apply the Gauss Jordan elimination method, the first step will be to make you will scale this uh, first row. Okay, so for scaling this first row, we will divide it by 3. Okay, so I will take this value and then I will divide it by 3, which is this value in the same over here, and then that will make it as 1. Okay, so yeah, this is the same as my answer before, and the second and third rows will remain the same. So can you see the Excel, what I am doing on Axel, can you see it?
Yes.
Okay. The next step is to make these two coefficients as 0. Okay, so for this, what you will do is the first row will remain the same in this new coefficients. Okay, first row will remain the same. Now we have to make it 0. So for to making it 0, what I will do is I will take this value, okay, and then I will add negative of this value, okay. I will add negative of this value. That means negative of this value k6. Yeah, and then multiplied by 1. So that will make it 0. Okay, so in this case, I will get these values. Okay. So similarly for this row, if I want to make this 0 0.3 as 0, so what I will do is I will take this value is 0 0.3, and then I will add negative of this value. That means negative of this 0 0.3, okay, and then times plus 1, okay. So I have to this and then times this first value. So that will make it 0. So okay, so it will be like that. Okay, so now you can see that these two steps I have repeated. So in this first equation, in the from this initial form, I first made this uh, made the changes in this first row, okay, by dividing it by the pivot coefficient, so it will be 1. And then I made these two values as 0, okay, so by the row operation. And then these row operations I will repeat, okay. So we have got up to like this kind of situations. So in the next step, I will make this 7.003 as 1. That means I will divide this second row by 7.0003, and then I will get this equation. So this system of equation and then this system of equation are the same, except that I have divided this second row by 7.0033. And then I made these two values as 0, okay, by the row operation. Okay, so I have got this equation system. And then after doing this, then I got is this one. Then next step is to, because this is the pivot position, I have to made it as 1. So I will divide this third row by 1 by 10.012. So I will get this. Okay. And then I made these two as 0. Okay. In this case. And here on this right left hand side, I will get an identity matrix 1 0 0 0 1 0 0 1 0. But these coefficients will now give us the direct solution. So this will be the value of x1, this will be the value of x2, and this will be the value of x3. Okay, so in Gauss Jordan elimination, then there are two operations which you will repeat after row. Okay, so if there are three rows, so you will operate these two sets of operations row after row. That means make the uh, pivot coefficient as 1 and make the coefficients above and below the pivot coefficients as 0 by the row operations. And in the end, you can get the result directly. So this is the Gauss Jordan elimination method. All right, so that was the Gauss Jordan elimination method. So gradually you can use these results. So thus, as depicted in this equation, the coefficient matrix has been transformed to the identity matrix, and the solution is obtained in the right hand side vector. Notice that no back substitution was required to obtain the solution. Yeah, in the simple Gauss elimination method, then we don't do these many operations on the matrices. So we need a back substitution method to get the solution. But in this case, everything has been taken care of. So no Gauss substitution is, no back substitution is required, and the solution is obtained directly. Okay, so that was it about this topic. Next, we will start the lecture number 7 about the LU decomposition and the matrix inversion. Okay, so that's all for today. Do you have any questions?